Hi, Mr. Smith here. We're going to discuss general relativity. Special relativity was described as when things are moving fast and the trees are going by. General relativity really comes into its own light when things are very massive and the warps in space-time are correspondingly severe. So here's an example. And this discovery was made by yes? Thank you. So this guy, Schwarzschild, was discovering Einstein's theory on gravity in addition to his own theories discovering projectiles in World War I. And Einstein had just put the finishing touches on general relativity, but then Schwarzschild put the finishing touches on a perfectly spherical star warping space and time. Schwarzschild sent his results to Einstein, and it was presented to the Prussian Academy. All right, so the warping that was schematically illustrated was known as Schwarzschild's solution, and this reveals a stunning implication on relativity. It shows that if a star has a small enough region, if its mass is divided by its radius and has a critical value, the resulting space-time is so dramatic that anything, including light, that gets too close to the star will be unable to escape its gravitational pull. So these were initially called dark stars. A more catchy name was coined by John Wheeler, who called them black holes. Black because they cannot emit light. Holes because anything getting too close falls into them, never to return again. Okay? And that's the name that stuck. So any object that passes at a safe distance are deflected, just like an ordinary star, and they can proceed on their merry way. But objects of any composition that come too close, okay, that this has been termed by the black hole's event horizon, will be drawn in towards the center and subject to an ever-increasing and destructive gravitational strength. So if you dropped in head first, you would find yourself getting increasingly uncomfortable, and the gravitational force would cause the pull on your feet to be much stronger than the pull on your head. So if you on a first feet fall, you're always a bit closer to the black hole's center. Okay, so much stronger that obviously you would be, your body would be torn to shreds. Yeah. So anyway, Schwarzschild unfortunately died a few months after discovering this solution. He was 42 and he died of a skin disease on the Russian front. So let's move on to another example, because that kind of ends the discovery that we made here. On the whole universe, the evolution of the whole universe, Einstein showed that space and time respond to the presence of space and time. So other cosmic bodies moving in the vicinity of warps, by the virtue of their own mass, has a further effect of the warping of space-time, which further, using the equations from general relativity, you can describe a mutual movement of space and time and matter quantitatively. The overall size of the spatial universe is changing in time. That's the fabric of the universe stretching, or shrinking. But it's not just simply staying put. And the equations of general relativity show this explicitly. Okay? In one example, there was an eclipse of the sun, and it allowed Einstein and his scientists to look at stars when it's daytime because the sun was gone. And they saw that the stars were not in the same position as they are at night. And that shows that the sun bends light. You just don't see it because during the day you can't see the stars. All right? So this is, of course, general relativity. It's just a theory. And there's no deviation from this that's been found with our present level of technology. So only time can really tell us if greater experimental precision would ultimately uncover some, thereby showing this theory to be destroyed by a child, not Schwarzschild though, you know, these children here, okay? And so this kind of alludes us to the next concept, which is called quantum mechanics, and it's just gonna knock your socks off. The special and general and Newtonian stuff is just out of the water, all right? So general relativity appears to be fundamentally incompatible with the next concept that we're gonna introduce, quantum mechanics, all right? And just regarding this material, it just prevents physics from understanding what really happens to space and time. And when matter gets crushed with space and time, fully at any moment, more generally, the conflict alerts us to a fundamental deficiency in the concepts of nature. All right? But, you know, being aware of this conflict, it's the central problem of modern physics.